Нет, вы просто не знаете немецкую технологию, как бы. Ну да. На самом деле, так сказать, хоть и государство у нас не дружественное нынче, но это не значит, что не нужно пользоваться хорошей наработкой. Вот. So let us start. So we discussed Borel fixed point theorem. Проверите, нас видно, слышно? Ага, спасибо. So on previous class we have discussed the following theorem. That if G is affine connected solvable algebraic group acting on complete variety X, then the set of fixed points is not empty. Well, as the variety, yes, of as algebraic variety. And as a corollary, we get that if K is algebraically closed, then even we have, so this set of points is just the set of points over the field is not empty, so there are fixed points. So since we mean by fixed points precisely the points that correspond to the maximal ideals, so that now this theorem says that if K is algebraically closed, we have these fixed points.
So, I have a question
about
this theorem. What is X, which I know that it's kind of fixed points, but when we
it's a variety. We have defined on our previous classes, we have proved that this is closed algebraic variety in X.
No, we have proved that it's closed algebraic variety.
Yes, but it could be empty. Yeah.
No. By definition, it's a set of points, and then we give the structure of variety.
No, by definition, it is it is solution of equations of the system of equations. It could be finite or infinite, but I mean, so you cover X by the charts, and on each chart, on each affine chart, it is the intersection of Xj with Ui is given by the system of equations.
This equation for each element of group. This equation for each element of group.
Нет, ну, в смысле, что если вы хотите, да, вы можете еще, ну, как бы задать это так. Но опять же, это, ну, скорее вам надо, ну, мы в прошлый раз вот, ну, как бы написали как правильно это задать, ну, как бы не пользуясь именно элементами группы самой.
Variety that we obtained is same that if we define physical equations of Jx equals x.
Yes, yes, yeah. Yeah, so the problem is that it can happen that you do not, I mean on the group of course there is unit element, but just saying that you are taking all elements over the field, for example, over R, it's not enough to define fixed point set for algebraic group. Ну, то есть, если вы напишете, ну, например, как бы возьмете, вы думаете о группах на C, но они могут быть определены над R, то есть, ну, как бы определены уравнениями с коэффициентами из R. И вот то, как вы хотите, как бы, ну, вы говорите, да, надо взять элемент из группы и написать, ну, gx равно x, да? Но, да, но тут есть небольшая тонкость, но как бы вот если вы напишете это над алгебраически замкнутым полем, это будет эквивалентное условие. А так это надо просто, ну, написать как, не надо говорить для точек, да, ну, как бы, а надо говорить, что это вот, ну, как бы система уравнений для группы на x, да, ну, то есть внутри группы умножить на x, то есть вы вот, ну, как бы, тут мы не должны говорить, что там, что gx равно x для всех элементов группы, потому что, ну, как бы, вы можете, например, эти элементы брать над R или брать над C. Это не всегда как бы... Да, ну, как бы, но тем не менее, вот это вот, ну, если вы думаете о G как, ну, каких-то, ну, это может быть записано уравнение в терминах, ну, как бы, уравнений на группе и на X. То есть, как бы, вот так. Ну, то есть, ну, мы это записали в том виде, ну, на прошлых лекциях, в том виде, вот как это надо понимать. So, what I want to just prove now is to prove that, so suppose B is the Borel subgroup. A Borel subgroup, because there are many Borel subgroups, and I just take one of them. So it is maximal connected solvable maximum connected solvable subgroup of G. Yeah, so notice that we have also introduced radical. Yeah, so radical of G. So do not confuse it with radical. Yeah, because radical is maximal connected, maximal solvable without connectedness assumption. Maximal solvable normal subgroup of G. Yeah, so I will explain. Yeah, so when you are speaking about the groups, yeah, so when you are putting the word maximal usually, so you use it within conditions. Yeah, so you use the maximal. So you attribute the word maximal to the maximal subgroup with these conditions. Yeah. So I mean, otherwise I should say it as follows. So B is the Borel subgroup if it is maximal and has the following properties. And here we attribute the word maximal with the following property. So with among the groups with the following properties. So maximal among the groups with the following and of course, it can happen that this subgroup is not maximal. So it can not maximal as the subgroup for a stupid reason. If your group G has connected components, then of course B lies in the connected. It can happen that B lies in the corresponding connected component, and this lies in G. But later we shall prove that it is really maximal in the sense of inclusions of the group if G is connected.
B is not can be a whole
And, yeah, and actually, yeah, so we also here do not, so of course in the algebra we are referring the notion of maximal ideal to be maximal among ideals that do not coincide with the ring. Here we are not so we do not care if B is equal to G or not, so B can be easily. So if G is solvable and connected, B is just equal to G. And so remarks. Yeah, so I wanted to state the theorem. Yeah, so just I didn't state the theorem that B is the Borel. So if you take this Borel subgroup, then the quotient G mod B is a complete variety. A complete variety. Actually, it is also projective. So, and let me write down these remarks. So, in general, the radical of G. Yeah. So, since so the radical, we do not assume that it is connected. So that means that we can only say that connected component on radical sits in B, and as well as connected components of the center. Yeah? That sits also in radical because the center is clearly solvable. It is a billion.
Why is projective invariance in the theory?
Because it will be it will follow from completeness, but it is stronger than complete, than being complete.
In condition of the theory,
I mean, we shall prove that it is complete, but we shall also derive that it is projective. So, what was I shall derive projectivity from completeness, and also so just it can happen. So if G is solvable and connected, then just B is equal to G, and here of course there is unique choice. Yeah, so such B is unique. Yeah? And the question is that actually, one can notice the following, that this condition is if and only if. So if G is connected, then G is solvable if and only if G is equal to B. Yes, so let us put it as an exercise. So if G is connected and solvable, so if G is connected, then there exists a unique Borel subgroup maybe it's not so easy. We shall prove it later. So, okay, so let us prove this theorem. So prove. Yes, and now we're proving it. Yeah. So, what is so how we are proving it? So let us start with noticing that so G mod B is homogeneous space. Yeah? So you can by Chevalier theorem, so we can embed. So there exists in V and the embedding of G mod V in the projectivization of V, such that B is the stabilizer of some vector. Yeah?
Maybe embedding of G, not explosion.
Ну как-то. Ну, не, ну, во-первых, теорема Шевале ну, говорила именно след. Ну, в смысле, она как раз стабилизатор точки G на B. Ну, в смысле, что, ну, E на B, у вас есть класс E на B внутри G по B, и B как раз стабилизатор. Ну, в смысле, это те элементы G, что GB лежат в B. Ну, как бы отсюда следует, что G из B. So, this is so this is a stabilizer of the line. Yes, so this means that if you act by B on this vector, it will be just the character. So the vector multiplied by the character. And notice that just if so since B is solvable, yeah. So notice that a posteriori. Yeah, so I shall now derive the projectivity out of completeness. So assume that we proved that G mod B is complete as the variety. Yeah? So that this will imply that if you have an arbitrary embedding of G mod B in projective space, yeah, so this will be closed. So it will be the image will be complete. So it will be complete. And we proved that if you have x and y is separable, then f of x and the x is complete, then f of x is closed. So X G mod B is a closed subset, so it is projective variety. And this doesn't embed, so this statement, it is the property of the variety. It doesn't depend on the embedding you are choosing. So your thing is always closed whenever you embed it. So this means that it should be also closed in projective space. So, and it will be projective variety. So here you see, after you have found the semi-invariant vector, so then we notice that further application of Lee-Colchin theorem, so that by Lee-Colchin theorem, there is an invariant flag. Starting at V, this vector V. Yeah? Yeah, so you just apply, you take the quotient and then apply the Lee-Colchin theorem, yeah, so because B is solvable and connected. So you have the sequence of so V1, V2, V3, and this is complete flag, yeah, so that dimension of Vi is equal to I. And then you do the following trick. So you prove first this theorem for the group of maximal dimension. Yes, so that first prove that G mod B is complete for B of maximal dimension. Yeah? Maximal possible dimension among Borel subgroups.
So we don't get those, they all have the same dimension.
Yes. Before we have this variety, we do not know it. All Borel subgroups. And this implies the following. So let us take this precisely this orbit. I mean, and you apply, so you take B of maximal dimension and you apply these two steps. Yeah? So then apply these two steps. So what do you get? So what about this orbit in P of V? I claim that it is closed. Yes, so just we claim that it is closed. Yeah, for the following reason. So notice that G of V1, yeah, sits, so on P of V you have action of GLV. Yeah? So it sits in the corresponding orbit of, yeah, so, yeah, so now, yeah, just, yeah, so, sorry. So, yeah, so, yeah, so let us put, yeah, so let us notice that also we can now consider action of G on the flags. Yeah, so that actions of G on the set of flags of maximal flags. And you notice that on the maximal flags on the vector space. And so I claim that, so you just take this to be I call this some flag, so let us put it, so let us take this flag, and so you take, so I claim that if I take this flag, the stabilize, so just I claim that this orbit is closed in the set of flags. So notice that yeah, so this will actually, yeah, so notice the following, so that the stabilizer, that saying that G stabilize the flag. Yeah, so just if you, I mean, if you have the group that H, so if you have the group that stabilizes the flag, just the subgroup in G. Yeah, so this implies that it stabilizes actually each element. Yeah, so then it means that H Vi sits in Vi for any I, and yeah, so for any H, so I'm saying that just elements stabilize the flag. Yeah? So H stabilizes the flag. If it stabilizes all the vector spaces, I mean maps of the vector spaces in itself, and in particular, H of V1 sits in V1. So this means that H
Could you recall what? So I remember the Chevalier theorem, but I don't remember the Colchin theorem.
yeah, so Chevalier theorem says that any G mod H can be embedded in P of V as the just stabilizer of the projective line. Yeah? And the Lee-Colchin theorem says that if you have the solvable group, then and connected solvable group, then you have the invariant flag. So I mean that you have, we're proving that it has the invariant vector on the vector subspace, but we can do the following: take V, factorize it by eigenvector. Yeah? So the vector space generated by eigenvector, take there a new eigenvector, etc., and proceed.
But
So
I
this
think that B is solvable
by assumptions.
here, and so the Colchin theorem can be applied. Yeah.
Yes, but also you can do the following small trick. You can assume that you start, I mean the first step of Lee-Colchin theorem can be rather arbitrary. There can be many eigenvectors. Yes, so if you are speaking about the formulation of Lee-Colchin of taking the flag. But since the Lee-Colchin theorem was the operation of doing, of constructing this flag was obtained by taking eigenvector and taking the quotient and just doing this procedure, you can start your flag with any eigenvector you want.
Vi
Yes, you are right. So this means that if H of V1 sits in V1, this means that H belongs to B. And B stabilizes the flag. So this implies that just... Что?
In particular,
Нет. B уже взято, которое стабилизирует вот этот флаг. Поэтому из того, что вы знаете, что H просто подгруппа... вот у вас условия, что B стабилизировало V1, вы вывели, что B стабилизирует флаг. Но это не значит, что в B содержатся все элементы, стабилизирующие флаг, если она просто какая-то группа со всеми условиями. Но на самом деле из-за того, что вы стартовали с V1 и V1 в точности равен стабилизатору в точности B, вы получаете, что B стабилизирует флаг. Да? Да, so this implies that B is equal to the stabilizer of this flag in the group G. Yeah, so in our group G that acts on the flag. Now you act by G on the set of flags. And notice that since the flag given a flag, you can reconstruct a basis, yeah, corresponding basis to this flag, and any basis can be mapped to any basis by the group of linear maps, yeah, so invertible maps. This means that G. So G sits in one orbit. So you have GLV acting on the set of flags. So this orbit is form the full set of flags. So this is set of transitive. There is a stabilizer, so it cannot be exact. So the set of flags, of full flags in V. Yeah? So this is one orbit, and this is a subset here. But notice that the set of all flags is a closed projective variety. So it is sufficient to prove that, to understand that this is closed. Yeah. Yeah. So what just I intended to do here. Yeah. So I want to prove that this orbit is closed, but assume that. But what can be said about the stabilizer? So the stabilizer of a flag is triangular matrix in some basis. Yeah. So that it is solvable. Yeah? So notice that just assume that G of F is not closed Yeah, so that means that there exists some flag in the closure that sits in the closure. And this implies that dimension of GF is less than, strictly less than dimension of G of F. But this is just, so this set is just G mod B. And this set is just equal to G mod H, but H is obtained as follows. So you take the stabilizer of the flag in GLV and simply intersect it with G. So this means, but the stabilizer of the flag, yeah, so it sits, of course, in the stabilizer of the flag in GLV. And this is solvable subgroup. Yeah?
How did you get this inequality of dimensions?
Но если орбита лежит в замыкании, то ее размерность меньше. Да?
Почему орбита лежит в замыкании?
Не, ну потому что если GF не замкнута, тогда можно взять точку в ее замыкании, значит.
Ну, орбита-то может быть, в принципе, лежит
Ну,
вне замыкания.
ну как, если вы берете точку в замыкании, то дополнение к замыканию инвариантное подмножество. Поэтому.
Дополнение к замыканию инвариантов может?
Ну да, ага.
И еще эта орбита не может внутри самого GF располагать каким-то.
Ну да, поэтому как бы, но это, оно лежит в каком-то, ну, G от F открыто. So G of F is, yeah, so of course the question why G of F tilde lies in some proper closed subset. But notice that here you have G of F, so the complement of, so the orbit is, we proved that it is itself open in its closure. So the complement is a proper closed subset, so it should have dimension less than the corresponding. Yeah, so this we proved.
Is it about irreducibility?
It is about constructibility. Open in its closure. That orbit and so this implies that yeah, so and notice that this is solvable group, so this means that H is solvable in G. Yeah? So of course you can pick up connected component, so and calculate the dimension. Yeah? So notice that since yeah, so H0 is connected solvable subgroup. Yeah? Of G. And now we are actually almost, so we are almost finished. Now you just have to compare the dimensions. So you take, the dimension of this one and this one. So you have that dimension of G mod H is less than dimension of G mod B. Yeah? And this implies that opposite equality, that dimension of H is bigger of dimension of B. And of course, this is equal to dimension of H0. So we get solvable subgroup H0, so connected solvable subgroup H of larger dimension than B. So this then you will get contradiction. Yeah? And this means that G of F is closed in some projective variety. In projective variety. So it is complete. Yeah. So so the thing is that why I'm stating completeness separately. So why I'm not just saying not considering projective varieties. Yeah? The problem is that it can happen that you take a projective variety, take its image under the morphism. It is still complete, but it is not projective anymore. So the property of being projective is not preserved under the morphisms. But complete, I mean, the notion complete, it preserves under the morphisms. Okay? And the last part is to understand what happens for other groups. But this we have already done. Yeah, so we have now we have proved that if B is a Borel of maximal dimension, then G mod B is complete. And out of this, we proved that if you have some variety which is already complete, so we have proved that if H is solvable and connected, then there exists G such that GH, G inverse sits in B. Yeah? So this we proved previous time. But just by taking fixed points in G mod B and noticing that H is fixing coset is equivalent to say that GH, G inverse sits in B. And this implies, of course, so since this group is also solvable, of course, this and connected. Yeah? This implies that if H is Borel, then this implies that just it is maximal. So after conjugation, it cannot be contained in B because the inverse conjugation makes H to be the subgroup of a solvable group. So this means that just GH, G inverse is equal to B. So
you say that we can't prove this without this variety G mod B.
Yes, you cannot prove this without this variety is complete for one group, for one B.
And where we use it.
What? Completeness?
Yes.
Yeah, so let us recall the proof. So
It was
we just,
this part, yes.
yeah, so exactly, so it is very, I mean, since it is very short, let us recall it. I mean, just take by Borel fixed point theorem, so you have the action of H on G mod B, which is complete. That maps, so H element maps the coset into HGB. It has a fixed point, so has a fixed point. And so over K bar. Yeah. So this means that, yeah, so this the saying that you have fixed points, this means that HGB sits in GB, precisely the same coset. And this, so you can move, so HG sits in GB, and this implies that H sits in GB, G inverse. So H sits precisely in GB, G inverse. Yeah. So you need only the fixed point on this coset, precisely as we do with Silo theorems. Yeah? Okay.
Can you
Uh-huh.
why the orbit lies in
If it is not, where? In the set of flag, right?
ну вот мы сказали,
Да.
что вот, когда Ж действует на X волной,
Да.
почему тогда орбита, она лежит в замыкании Ж?
Нет, мы просто мы берем вот наш тот флаг, с которого мы начинали, стабилизатором которого является B. Yeah, so we take the flag, which is the stabilizer in G is precisely B. Yeah? So we assume that it is not closed. So if it is not closed, there are points in the closure which is not inside this orbit. You take this flag, just take this flag as a point inside this set and consider its orbit. It is so since any orbit is open in their closure, the complement is a proper closed subset of smaller dimension. Yeah? Ну, то есть, мы рассуждаем так, пусть орбита не замкнута. Если замкнута, то мы все доказали. Да? Замкнута в проективном многообразии. Тогда мы просто ее замыкаем, ну, это подмножество, и берем точку внутри замыкания, но не принадлежащей орбите. И берем там орбиту.
Вот почему если вы замыкаете,
Короче,
это
орбита-
приятное множество, да,
Короче, вот
Да.
орбита, она получается...
А орбита, она открыта в своем замыкании. Не, ну то есть как бы вот, если она не замкнута, вот как бы мы ее замыкаем, и вы что-то добавили. Берем здесь точку, берем там орбиту. Ну то, что мы добавили, очевидно же инвариантно, потому что замыкание — это объединение замкнутых подмножеств, которые содержат пересечение замкнутых подмножеств, содержащих данную орбиту. Очевидно, что такое множество инвариантно относительно сдвигов. Но сама орбита инвариантна, поэтому и дополнение инвариантно. Поэтому мы берем любую точку, берем орбиту там. Но вот что действительно тут как бы серьезно, и это надо доказывать, ну, то есть как бы нетривиально, что, ну, могло бы так получиться, что, ну, как бы, что вот это вот само множество, оно дурацкое, ну, как бы оно не открытое в своем замыкании. И тогда бы, ну, потенциально могло произойти так, что...
Там внутри
что вот там в дополнение вы взяли множество, а оно не содержится в замкнутом подмножестве. То есть как бы вот, чтобы говорить, что вот эта размерность меньше, строго меньше, надо, по крайней мере, знать, что вот эта вот вещь содержится в каком-то замкнутом подмножестве.
Надо вспомнить, что это замкнутое, оно дополнение к плотному открытому или просто к открытому.
Ну, оно к плотному открытому дополнению.
То есть плотность там будет всегда?
Ну, потому что вы замыкание берете. Плотность есть всегда при замыкании. Но открытость, как бы, чтобы говорить о размерности, да? Не, ну потому что там, как бы, когда у вас какие-нибудь топологические пределы, то там могут быть, ну, да, достаточно там дурацкие множества.
It seems you have already proved that G quotient B is a projective. Why do you need that remark on it?
Because it is separate. If you know that, yeah, so of course I knew this, but separately it is very convenient to know that if your homogeneous space is, so the homogeneous space is complete if and only if it is projective. I mean that if you are speaking about properties of homogeneous spaces, you can ask what types of varieties you can get. So if you say that your variety is complete, then automatically it implies that it is projective. So which is good point. I mean, you do not need the particular embedding for this. Yeah? And actually, a priori, so this should be, I mean, if you have a projective, so the property of complete variety, so as the separate notion, implies us that the image of complete is complete. So otherwise, I mean, if you do not use the notion of completeness, it's not clear that if you take projective variety and take its image under the morphism, it is also closed. I mean, you have to, you have to prove it separately or refer to this separate notion, which is more convenient. Okay? Yeah, is it clear now? Yeah. So, yeah, and no questions? Yeah. And now I want to, this implies that you have precisely the, so the set of Borel, so far what we have proved that more or less that the set of Borel groups, so the set of Borel subgroups yeah.
Did we prove that the connected component of identity is a subgroup?
No, yeah, so we didn't prove it, but it is easy. I mean, it's easy, just it is an exercise. Yeah. So, yeah, so the set of Borel subgroups, they actually, so this is a claim, they correspond to the points on G mod B, and the correspondence is clear. Yeah, so if you have given B tilde and B, there exists G in G, yeah, so such that GB G inverse is equal to B tilde. And notice that, of course, if you take, if we take G from the same coset, G tilde from the coset GB, we get the same result. Yes, so then G tilde G tilde B inverse is just again B tilde. So actually what is actually all such G tildes, so such G tilde belong to the normalizer of B, yeah, in G. But later we shall prove that if G is connected, then normalizer coincide with B. Yeah, so just later we shall prove that if so connected that G is that normalizer of B in the connected component of G is equal to B.
G tilde comes from B, then
I mean, if G tilde comes from the coset, I mean, you change G by, you change G by any element of B. Of course, it doesn't spoil this inequality, yeah? This equality. But of course, what is used here, that G tilde is in normalizer. Yeah? I mean, this equality holds if and only if G tilde is in the normalizer.
but there is B and there is B tilde.
I mean, if you have two solvable subgroups, so two maximal solvable subgroups, two Borel subgroups, then they are conjugated. Yes. So what is the ambiguity of the choice of G? So you can choose a G up to the multiply G by any element from the normalizer.
Ah,
Yeah?
so not G tilde in normalizer, but
Yeah, so not G tilde on normalizer, but this happens if and only if we take G from the normalizer of in B.
неправильно написано, что G принадлежит числовому само. Например, все источники.
Ну да. Мгм. Нет, да, ну в смысле, да. Ну в смысле я вот это имею в виду. Okay. So later we shall prove that the normalizer of connected component coincides with B. So this tells you that the set of Borel subgroups are in bijection with the cosets of G mod B. Okay.
What is the normalizer of the subgroup?
Yeah. So there is a standard actually. So you can speak always of the normalizer of the subset if you have y and x. So y is a subset in x, so that normalizer of y in G is the set of elements of G such that Gy sits in y. But notice that if you have the group, the subgroup of G, yeah, so there are not so many actions on that comes from G that you can act on the subgroups. And the only action is just action by conjugation. So the element of G acts by conjugation. So the normalizer of G is just the set of elements in G that preserves this set. Yeah? Just the elements of G such that GH G inverse sits inside H.
Why would so if we consider like left action or right action, then
The group won't be mapped to the group. It will be mapped to the coset.
you
Там
mean
единицы нет.
normal.
Нет, если H... Нет, вообще у вас есть только, ну, как бы, из естественных действий, ну, как бы, без дополнительных требований. У вас, да, есть только одно действие, которое подгруппу переводит в подгруппу.
В какую-то другую?
Ну, в какую-то другую, но все равно в подгруппу. Ну, это же H, G минус 1.
В смысле, мы рассматриваем действие сопряжением на группе и то, куда переводится подгруппы под действие.
Да, но при таком действии подгруппы всегда переводятся в подгруппу. Да?
Да, получается...
Ну, если вы вообще возьмете любой автоморфизм G, ну, как бы, то подгруппа перейдет в подгруппу. Но
Получается, правильно я понимаю, что
Да.
G от H это все элементы, когда G от G минус 1 равно H?
да, ну,
Значит, что это включение на самом
на самом деле это равенство.
То есть просто это все такие элементы, что сопряжение именно эту подгруппу оставляет как неподвижную точку.
Да, но может двигать элементы внутри нее. Да.
Элементы этой группы, но сама группа остается.
Да.
Прикольно. И получается, что мы рассматриваем нормализатор B относительно действия связанной компоненты.
Это связанная компонента, это вот, чтобы не оговариваться про связанный G, да, ну, как бы,
Только сама борелевская группа, сопряжение только самой борелевской группы оставит ее на месте.
да,
Все остальные будут ее выкидывать куда-то.
в другую борелевскую подгруппу. Поэтому их как бы очень много. Ну, то есть это, что... So in particular, this will imply that if you have one Borel subgroup in G, then G will be normalizing it, and this will be contradicting this the fact that any element of G that is outside of B should map it outside.
Если борелевская группа одна,
То она просто совпадает связанный компонент. Но это мы потом поговорим, это важно. So also one can ask how we can construct how we can obtain Borel subgroups of algebraic groups. Но она одна с точностью до замены координат, а это и есть замена координат, это и есть сопряжение. Да? Ну, то есть мы so on previous class we have proved that for GLN the group of triangular matrices is the full group of triangular matrices is a Borel subgroup, and it was example of Borel subgroup for us. And just the fact that they are conjugated really tells us that, of course, so conjugation is just changing the basis from the viewpoint of our operators. Yes? So this means that simply all other groups are obtained by choosing a different basis. But in fact, it is just choosing a different flag that they fix. And moreover, notice that it can happen that one group can fix quite different flags. So if you start with eigenvector, so because one group can have a priori many eigenvectors. For example, you can start with diagonalizable group and take any eigenvector in the beginning of the procedure of constructing flags. So, and what I want to tell you now is how to obtain to describe Borel subgroups in practice. So in practice, just it is. I do not give practical algorithm, but I mean, what is the general form of the group of the Borel group that you expect? So it is the following theorem. So theorem. So suppose you have G is this subgroup of GLV. Then there exists basis Yeah, so notice that the set of triangular matrices depend on basis. So there exists a basis and such that so that defines the group of triangular matrices. So that defines the group of triangular matrices. T and V. N is the dimension. So such that intersection of G and this group of triangular matrices is just Borel, a subgroup of G. And any Borel subgroup of G can be obtained this way. Yeah, so notice that this is not completely trivial statement. So
Is it partly trivial? I just don't understand why. How can it be proved?
yeah, so of course a part of it is trivial. Yeah, so because if you take Borel subgroup, yeah, so just you take a B inside G, yeah, then then you do the following, so you can trigonalize it. Yeah, so just trigonalize.
Why does this trigonalization have any relation to the trigonalization of GLV? Or maybe something?
Yeah,
Some relation between
because because trigonalization, we're just performing trigonalization on the assumption that B is the subgroup in some GLV. Yeah? So you see that in some basis B will be triangular. So this means that you can just pick this. So at least B is the subset of some triangular matrices. And then you just intersect it with G. Yeah? So this is a solvable subgroup. And this implies that connected component of this group coincide with, yeah, so just, of course, here we have to take connected component. So connected component of this group coincide with B, yeah, because B is supposed to be maximum. Yeah. So this is this follows precisely by our previous theorems, and you see that you just yeah. So yes, just yeah. So you just apply Lee-Colchin theorem here, and you get that if you want to do something in practice, so there is the question of describing the Borel subgroup. The question is of choosing the right basis where this group will be triangular, and it is actually most convenient way to express Borel subgroup. So, for example, just the example is the following. So you can so usually when you're speaking about orthogonal groups, so when one speaks about orthogonal groups, you take the standard bilinear form, yeah. So you take just there is a slight problem because bilinear form is just is denoted by B, yeah. So then take this bilinear form and just you define O of V to be the group of group that preserves this bilinear form. Right? So, for example, over C. And so this form of this form is not very convenient, because if you want to speak about the Borel subgroups, it is not clear how to draw it and what relations on the elements you should write down. But notice that there is another choice, so at least over C, so another choice of basis.
So the example that you take, you need to group with one element and ask which...
Нет, это билинейная форма. Ну, О сохраняет эту билинейную форму. Да, да, ну, которая сохраняет эту форму. Да, да, да. Ну, в смысле, что она, ну, вот так ее сохраняет, да, при вот таком действии. Но почему я так пишу для единичной матрицы? Потому что сейчас матрица будет не единичная, конечно. Потому что, so the problem is that when you're speaking about this basis, since it is not related, so it's not as good related as it should with just with invariant flags in it. So the idea is to choose another basis, so the form that looks like this. So this is also symmetric form. Yeah. So it is a different diagonal. It's not even two blocks. It is just precisely written as the different diagonal.
C
Hmm?
over C of quadratic of same.
Ну да, да, ну как бы, конечно. So I have just. So we see they are the same. So this form is of course the just particular just it is equivalent to this form of just if you take these two vectors first and last for the basis of 2 and you do it like this, so going from two directions, so you get in this different basis, you get this just hyperbolic forms. And so this form is hyperbolic. So of course, over R or over finite field, they can be not equivalent. But over R, they are of course not equivalent. So this is another choice of form. So here one can notice that just one can write down intersect O of V with triangular matrices, and there will be a triangular group with some conditions, but one can notice that only the half of, so one half of the elements depend on the others. Yeah, so that just there is a relation between these coordinates. That allows you to calculate the dimension of the group and prove, so that allows to calculate the dimension.
So we can see that we have found a good basis if it's enough dimension of intersection.
Yes, yeah.
But we don't know the dimension of this intersection.
I mean, if you prove that the relation that fixes this form is just it uses only half of the elements in the matrix, then you prove what is the dimension of this group. But actually, it's more convenient to pass to Lie algebras. And
How we know that in this basis this intersection is really Borel-Sabukov from dimension?
so at least the intersection of upper triangular matrices and the group that fixes this form will be solvable. Yeah?
It will always be solved.
It will always be solvable because it is a subgroup of a solvable group of triangular matrices. However, it is not so clear what is. It's not so clear that it is Borel subgroup, so that it is maximal. Still, it's not clear. So, and it wouldn't be clear until we're able to recalculate the dimension of the Borel subgroup via some data, via some dimension of some data related with our group. But the idea is that you can just do it. I mean, at least that you can prove that it is solvable by knowing the dimension of expected dimension of the Borel group and proving that precisely this gives you the example of solvable group of prescribed dimension.
Is it an example that if I take unit quadratic form, standard quadratic form, then no upper triangular matrix except unital matrix would preserve it. But
Yes.
if I take and rotate the basis and take another form instead of L, which I take the skew diagonal form, then I would take some kind of upper triangular
It's yeah. So
It won't be just unital, but more.
yes, yeah,
Rich choice.
yeah, yeah.
Is it what is the relation between coordinates here? I don't understand.
Не, ну в смысле вот эта форма, а вы имеете в виду вот как эта форма связана с этой? Ну вот эта форма, ну есть стандартная замена, которая меняет вот эту форму на вот такую, да? Ну что это такое? Вот это гипербола, записанная вот в таком виде, а вот это гипербола, нарисованная вот в таком виде. Да? То есть это поворот. Ну, x плюс y пополам.
Почему тут гипербола?
Ну как? Ну, потому что квадратичная форма равна единице, это гипербола, да? Над c.
Это x квадрат плюс y квадрат.
Ну, потому что над c они эквивалентны такой. Ну, как бы, ну, вы вот эту меняете на вот такую, а вот это эквивалентно этой. Да, все они эквивалентны. Ну, любая асимметрическая квадратичная форма эквивалентна такой, но тем не менее. Вот, но как бы вот такую легко написать по блоками 2 на 2, ну вот длинными блоками. А потом вы как бы делаете следующее, ну вы просто вот этот блок разгоняете. То есть это первый и второй вектор, вы его ставите первым и последним. Дальше следующий блок, второй и третий вектор, вы ставите вторым и предпоследним. И так далее. То есть как бы вот, ну вот такую матрицу вы разгоняете в эту, то есть это первый и второй ставите последним. Вот они так спариваются. Вот этот ставите вторым, а этот ставите предпоследним. И они вот так вот складываются.
Do you claim that not triangular matrix don't preserve this form? No.
We can intersect matrices that preserve this form with triangular ones and get a plus of both. It's not whole.
Да. Ну, то есть это маленькое будет множество.
Половина размерности.
Okay. Yeah, so and the same can be done with symplectic form. Yes, so it is not standard way to write down symplectic form, but you can do it like this. Yes, so you can put minus ones, and you can put minus ones below diagonal, so in these two blocks. And this will give you also the example how you can realize this triangular matrix.
So there would be half dimension as well of this situation?
Yes, so, well, it won't be a precise, yeah, so just from the viewpoint of diagonal, yes, so it will be just.
Это же одна и та же. Это же просто одна и та же.
Нет, ну тут как бы с точки зрения группы, ну как, это коссимметрическая матрица, это симметрическая. Ну как-то. Ну, у вас, ну, они совсем разные будут. У них даже алгебры будут разные. Ну, в смысле, как вы по элементу, который сохраняет коссимметрическую матрицу, построите элемент, который сохраняет симметрическую. Если вы говорите, что они изоморфны,
Эти же формы, они...
это симметрические формы, и они изоморфны. А это симметрическое, это коссимметрическое. Тип при линейных преобразованиях форма сохраняется. Любая форма — это сумма симметрической и коссимметрической, а тип разложения на вот эти в прямую сумму симметрической и коссимметрической сохраняется. Yeah, so it is a good point to make a break now, and we shall discuss some more theorems like density theorems, and then we shall pass to studying solvable groups in more details.